So, for our purposes, a probability experiment in the continuum is characterized by a density function, a function p of x, which connotes mass per unit length, or mass density at the point x. Of course, the density functions have to be non-negative. They connote probabilities after all, and they have to have unit area. This, of course, comes from additivity. You stitch together all the pieces, and you make the pieces tinier and tinier. In the limit, you should get exactly 1. What kinds of functions occur in practice? So let's go back and look at the very first one that we encountered through our coin tossing experiment, and this, of course, was the uniform density. This density has a rectangular function. So u of x, u for uniform, is defined formally on the whole line, but it has support only in the unit interval. It takes value 1 in the unit interval and is 0 everywhere else. It's manifestly non-negative everywhere. The only question then is it properly normalized? And of course, we've seen this, and to do a sanity check, let's run the integral through. The integral over the whole line of u of x dx, well, the only portion that contributes is the unit interval, because u of x is 0 outside the unit interval, and so that leaves us an integral from 0 to 1 of 1 times dx, and of course that just gives us the length of the interval from 0 to 1, or in other words, unit. So in fact, the uniform density is properly normalized. This density, which puts mass equally everywhere, is the natural continuous limiting analog of a combinatorial setting. And I've given you, for example, a generic combinatorial distribution on a set of possibilities, where each possibility has got the same probability. In the limit, as you look at a crowd of points getting closer and closer together, you end up with a uniform density, which has got a constant mass density in a certain region. The natural application domain for things like this go all the way back to Pierre-Simon Marquis de Laplace. And Laplace thought of the uniform density arising in any setting where we had a continuum experiment where there was random choice in some interval. Now, how do we go beyond this? A natural example is the exponential function. The exponential density, and I've now used the terminology g of x here, and that's because this density is connected to a family of densities called the gamma densities that the student will see in Tableau 10 Part 2 as she goes along. So let's use g of x for a temporal. It's just a name for this function. It stands for the exponential function in the positive half of the line, so it's a decaying exponential, and it's 0 on the negative half of the line. Again, it's manifestly non-negative everywhere. A look at the graph convinces you that yes, indeed, it's never negative. And what about its area? Well, the area under the curve is a very elementary integral. The integral of the function g of x over the whole line, well, has contributions only from the positive half line, because g of x is 0 on the negative half. The integral from 0 to infinity of e to the minus x dx is an elementary exponential integral. We run it through the mill, and out comes exactly 1 minus 0, or 1. The exponential density is also properly normalized. We should pause for a moment and ask, have I seen a function like this in the discrete domain? Cast your mind back to Tableau 6 Part 1. Did you encounter any kind of function with this kind of decaying exponential character? If you came up with the geometric distribution, then indeed this is exactly the discrete analog of this density. And again, the geometric distribution, as you might recall, has an exponentially decaying character over these discrete integer points. Where does this density arise? This puts more mass density near 0 and very little mass density way out for large values of x. In other words, the probability of taking a value somewhere near 0 is relatively high. The probability of getting a value, a random variable, which takes on a very large value is very small. This turns out to be the natural model for randomness in settings where we have queues, where we are waiting for something to happen, the time between two arrivals at a queue. This turns out to be exactly the way one models these problems. Still another example, and this one is not so elementary, but it is familiar to us. Constant mention of the bell curve in common parlance has led us to common acquaintance with this mysterious object. The normal density has got a form which is like an inverted bell. The function is nice and symmetric, and the explicit form is given by an exponential with a decaying quadratic in the exponent and a normalizing factor square root of 2 pi in the denominator. By a long tradition going back to Gauss, we call this function phi of x. Okay, now it's clear that this function is strictly positive everywhere. Why? Because the exponential function is always positive. So positivity is trite. It's not so clear that it is in fact properly normalized. Where does that mysterious factor square root of 2 pi come from? The moment you see pi, you start thinking of a circle perhaps, but there's no circle in evidence here. So is it in fact properly normalized? Indeed it is. But at this point, we've exhausted almost all the probabilistic intuition for this, and verifying that this function is in fact properly normalized to unit area becomes a calculus exercise, albeit with a little twitch to the tail. And so I will defer that for a moment. Where does this arise? Where is the discrete analog? And this is harder to say. The student might want to pause for a minute and say, among the examples we saw in Tableau 6 Part 1, is there anything where the function in the discrete domain looked something like this bell curve? If you came up with the binomial distribution, then indeed we found a discrete analog of the bell curve. It is not at all obvious that the binomial distribution, on the one hand, has a functional form which gives us anything like this bell curve for the normal density. That is not at all clear analytically, but it turns out to be a deep and powerful process of analysis which goes back 3 centuries and led to some of the most potent and fundamental results in the theory of chance. We will come back to this in our concluding lecture. Right? So for the time being, the normal density arises naturally in settings where there's any kind of central tendency, when things are being brought in to the center in some way. Notice the normal density puts more mass around 0 and relatively little mass far away from 0. Yeah. The bell curve turns out to be ubiquitous in the theory of chance. And it is ubiquitous through the agency of the mysterious central limit theorem, which, very roughly put, says that if you add enough independent perturbations, whatever that means, the end result looks approximately normal, looks approximately distributed as if it were drawn from a continuum experiment with this character. These are the basic densities, the 3 fundamental densities. Right? There are many others, of course, and in specialized circumstances you'll encounter different functional forms. Generically, we'll call them P of x. They are all characterized by the attributes that they have to be non-negative, they constitute a mass density, and that they are properly normalized to have unit area. How do you compute probabilities? Figure out the subset of the real line that constitutes the event under consideration, and simply look at the area under the relevant curve in that region.